Good morning, everyone. Welcome back. We'll get started now. So where we are today is we are in the midst of section 16.3. So I'll just back it up just a little bit so we can see where we are. So we're in 16.3 and we're looking at the fundamental theorem for line integrals. So you can think of this as kind of an analog to the fundamental theorem of calculus. The fundamental theorem of calculus it tells us that if we integrate a derivative, a derivative of a function, then we can work out the value of the integral by just sampling the antiderivative at the endpoints. So it's taking the difference of the antiderivative at the endpoints. The fundamental theorem of line integrals tells us something similar about integrating vector fields. So a line integral of a vector field along a curve. If that vector field is a gradient, then we can evaluate the integral by just evaluating the potential function at the endpoints. So that's what the fundamental theorem of line integrals is saying. It's just a sort of a direct analog of the fundamental theorem of calculus. In fact, it followed from the fundamental theorem of calculus. So when we're integrating a potential function, when we're integrating a gradient vector field, we just have to evaluate the potential at the endpoints. It's the analogous to saying if we integrate a derivative, we just evaluate the antiderivative at the endpoints. So we did proof of that following from the chain rule and the fundamental theorem of calculus. We did an example using the gravitational vector field and its potential function, which we worked out. Potential function is just hidden behind me here. And so we worked out the value of the work without actually having, in some sense, without actually having to compute the integral using our integration techniques. We just evaluated at the endpoints of the path at the potential function. All right. So this is the part I skipped over, and then we'll get to it now. So there's a few things to keep in mind now that we're talking about integrating over curves. And very soon we'll talk about integrating over the region inside a curve. Again, we've already talked about double integrals, but we'll come back to that concept. So just a few bits of terminology. A curve is called simple. So I'm just going to go through these one at a time. It's called simple if it doesn't intersect itself. So down below are just some examples. So on the diagram on the left below, the top one is simple because it doesn't intersect itself. The one on the right in the top row is not simple because it intersects itself, comes back and it intersects itself at a point. Now, the next idea is known as closure of a curve. So a curve is closed if its initial point is equal to its terminal point. So if it starts where it ends. So that, again, the top row, the first one is not closed because its initial point and its terminal point are two different points. Whereas the one right below it is closed. And it's also simple because it doesn't self-intersect. The only time it's going to have a point that is in some sense in common is the end point. So we refer to this as a simple curve, which is closed. The one in the bottom right of those four is not simple because it intersects itself, but it is closed because it does come back on itself again and forms a loop. So you can think of these as closed if they're forming a loop, not closed if they don't form a loop, and simple if it doesn't intersect itself, and not simple if it does intersect itself. We get the same sort of ideas for regions. So this is now not just the curve, but the stuff trapped inside of it. So we're now imagining that we've got a closed curve. So there's an inside region and an outside region. A region D is called open if for every point P in the region, there is a disk with center at P that lies entirely inside D. So that's what we're going to call an open region. So our open region would look something like this. I would dot the boundary because those cause problems. But for any point P in the region, I can always find a disk around it such that that disk lies entirely inside the region D. Now you can see why I've dotted the boundary, because if we did include the boundary, I'll draw it down in the picture down below here. So we've got a solid boundary. Suppose I consider a point on the boundary. There's no disk that I can draw around it such that it lies entirely inside D, because any disk I draw around it, no matter how small, is going to have stuff that lives outside. There's going to be stuff that's outside, and there'll be stuff that's inside. So when we're talking about an open region, we're typically dotting the boundary in, because the boundary points won't exist if we're dealing with an open region. A region is called connected if any two points can be connected by a path that lies inside D. So for example, this is connected because no matter what 2 points I have, there's always a way to get from one to the other. Similarly down here, this one's connected because I can always get from one to another by a path entirely inside the region. This one on the far right, not connected, because I can't get a path that connects them without having to leave the region. I've got to leave the region to get to the other side. So those are some bits of terminology about connectedness. And then we've got this additional, so all these definitions so far might be familiar to you already. You may have seen them already, may have used them already. Simply connected might be a term that's new to you. So what does simply connected mean? Simply connected means that every loop you draw only contains points in the region. So a region D is simply connected if every simple closed curve in D encloses only points that are in D. So this one on the top is simply connected because no matter how I draw a loop, it contains only points in D. How about the one down below? Well, this is not simply connected because here's a loop that I can draw. In other words, a simply closed curve. And there are points inside it that are not in D. That's that white region, that hole. Similarly, the next one, I can draw a loop. Actually, I could draw a loop like this if I wanted, and I could catch inside it a couple of different areas where it doesn't consist of points in D. So these regions would be called not simply connected. They have holes in them. So this idea of simply connected is really a question about whether there are holes in there. And the last one's not even connected. Okay. So let's go and see where these definitions are going to get used. They're going to come up in some of our theorems. It's just their assumptions we're going to be making about our domain. And so we're not going to scrutinize over them too much, but it's just good to know some of these definitions so that we know when our theorems apply and when they don't apply. Okay, so this is where we ended off last day. We were talking a little bit about these properties of conservative vector fields. And I just want to recap this, and then we'll prove this result, this number 7. So if F is a vector field over an open, simply connected region D, so that means it's an open region and it's got no holes in it, the following are equivalent. So F is conservative. In other words, it's a gradient vector field, so it has a potential function. The line integrals over any path from x0 to x1 is independent of the path chosen. So it only depends on the endpoints. And the line integral around any closed path in D is 0. So these are all equivalent. If it's conservative, the line integrals are path independent, and integrals around closed paths are always 0. Any one of these holds, all of them hold. That's really what it means to be equivalent. So if any one of these holds, then all of them holds. So if I have a vector field for which I integrate around any closed path and it's always 0, then I know it's a conservative vector field. And therefore I know it's independent of path. If I have a a vector field, which I know when I integrate it over any path from x0 to x1, it's independent of the path I take, then the vector field's conservative and the integral 0 around any closed path. So the circle around the integral in part C just means that it's an indicator to us that this curve C is a closed path. So we are integrating around a closed path. So it's just a visual indicator that says, hey, this integral you're looking at, it's not going from one point to a completely different point. It's actually going from one point back to itself around a closed curve. So we'll call this a closed integral, or a closed path integral. It's all right if you leave that off, no big deal. It's just a visual indicator that says that this curve C is a closed path. All right, let's get to our definition. What does it mean to be independent of path? I've sort of already said it a couple of times. This is what B really means. So this independent of path, that's in italics, meaning that we should really define what it is, but it might be self-explanatory. But here's the definition. If F is a continuous vector field within the domain D, we say that the line integral is independent of path if the integral along any path C1 is equal to the integral along any path C2, as long as C1 and C2 have the same initial and terminal points. So these are going to be equal for any curve C1 and C2 if C1 and C2 start at the same point and end at the same point. So you kind of visualize it like this. Here's a point, let's call it x0. Here's another point, x1. And we have a path that takes us from x0 to x1. That's our path C1. We can have another path that takes us from x0 to x1. And if the integral for any two paths from x0 to x1 are always the same value, they're always equal, then we say it's independent of the path. And this statement above says that you're only going to get this in the situation where the vector field itself is actually a conservative vector field. And then that means the fundamental theorem of line integrals applies, and the fundamental theorem of line integrals says you can evaluate the integral by just evaluating at the endpoints, and therefore you don't even need to worry about the path you've taken. That's where this result is going to get used for us. Okay, let's have, so maybe I should say what I want to do here is I want to establish the equivalence of A, B, and C. So that was a result. Let's actually see why it's true. So we have that. Maybe I'll jot it down here. The fact that a conservative vector field has line integrals that are path independent. This is the fundamental theorem of line integrals, which we've stated back here. I'll just jot it down, which is theorem 2. So the fact that A implies B, that's theorem 2. So we already know that A implies B, that if A is true, then B is true. And what we want to do is establish the equivalence of the rest. So what we'll do now is we'll show that B and C are equivalent, that if we have path independence or independence of path for our line integrals, then that means that the integral is 0 for all closed paths. And vice versa, if we have that the integral is 0 for all closed paths, then the integral is path independent, or independent of path. So this is what we want to show here. This is B implies C. And in fact, it's actually both ways, because there's an if and only if that this is B is equivalent to C. That's what we're proving here. So let's go ahead and give this proof. So we'll start with the fact that F is independent of, or sorry, the line integral of F is independent of path. So we're going to suppose that the integral of our vector field F is independent of path. And then we will let C be a closed path in the domain D that we're interested in. And so what I want to do is I want to show that the integral around this closed path C is 0. So that's my goal, is to show that the integral around C is 0. So what we'll do is we'll pick here, let's just draw what C would look like. C is looking something like this. There's C. What I'm going to do is I'm going to pick 2 points on C. Say x0 and x1. So I say points, I write down vectors, but we are fluent in both now that we can think of these vectors as representing, as being the position vectors of those points. We're not going to scrutinize over the difference of vectors and points in this case. If I say that these are the points, I mean these are the position vectors that give those points. So here's our situation. We've got these 2 points, x0 and x1, on our curve C. And what we know is that the integral along any 2 paths from x0 to x1 is going to be the same. So what I'll do is I will consider these 2 halves. Maybe I'll put one of them in a different color. So I'll consider the part of the curve C that goes from x0 to x1, which I've highlighted in blue, and I'll call that one C1. And then I'll call the other half C2. So I've just split C up into 2 curves. So let C1 and C2 be 2 curves on C from x0 to x1. And now what I can do with that is I can say, well, if I integrate along C1 of our vector field, then this has got to be equal to the integral along C2 of our vector field by independence of path. So these are equal. So that means that if I integrate along C1, and then I'll move this one to the other side, minus the integral along C2, then that's going to be 0. So I just move the integral on the right to the left by just taking the negative of it. And then the key thing to note here is that negative the integral along C2, much like it is for integrals in calculus 2, let's say, where I have a negative of an integral from a to b, I can switch the limits of integration, or in other words, integrate backwards over the interval, and that'll produce a negative of the original integral. So what I can do is I can integrate that second curve backwards over C2 and absorb the negative sign in there. So it's plus the integral, and we'll just by shorthand use negative C2 to indicate that we are going backwards over it. So I will put the negative C2 in green and just indicate that negative C2 would be just that same curve, only we're going backwards along it. That would be negative C2. And that's F dot R equals 0. And so now what this is saying is that if I integrate along C1 and then along C2 backwards, I get 0. But integrating along C1, then C2 backwards is just integrating around the curve C. And so that's equal to 0. And that's what we wanted to prove. We wanted to prove that the integral around C was 0. And we did it by path independence here. Yep, today's the last bit of material for the exam. Just these last few examples we're working on. So this is path independence, implying that every integral around a closed curve is 0. We can do the opposite direction. Suppose the integral around any closed curve is 0. So we're going to, similarly, if the integral around any closed curve is 0, so for all closed curves, then that means that no matter which two paths I take from starting point to ending point, the integral around the whole thing is going to be 0. So the integral over each half has got to be the same. We basically just reverse all the steps in this previous argument. So this would tell us that the integral. So that's why I've written this similarly here. Similarly packs a big punch. It's really saying just reverse all the steps above, and you'll see that the reverse is true, that the integral is path independent. So not much more needs to be done there because it's a similar or analogous argument. So this is telling us then that if we have path independence, then closed integrals or integrals around closed paths are 0. And if integrals around closed paths are always 0, then the integral is path independent. So that establishes B and C. So what we have now, I'm just going to scroll back up to those statements, is we have that part A, if it's conservative, then integrals are path independent. But we just established that B implies C. So moreover, if it's conservative, then integrals around closed paths are 0. Also, if we have integrals around closed paths, then integrals are path independent. The only thing we haven't established now is if B or C is true, then the other one is true. So if B and C are true, why is it that the vector field is conservative? How come there has to be a potential function? And that's the next theorem. That's this theorem here, theorem 4. If F is a vector field, and we have to have a few assumptions on it, it's continuous on an open connected region D. If the integral is path independent, then F is conservative. So there's a potential function. So path independence implies the integral, or sorry, the vector field is conservative. I will just refer to this as the proof is in the text. So you can have a read at the proof. What it is it's just really saying, okay, if it's going to be a conservative vector field, then you have to have a way to construct the potential function. And the way the potential function is constructed is by using an integral and really exploiting the fact that it's path independent. So you can choose the paths however you want, because that doesn't affect the value of the integral. And so you build up the antiderivative in some sense. You build up the potential function so that the gradient of it is f. And you build it using integrals and path independence so that you don't have to worry about whether your integral has changed values depending on the path you've taken. So you can see the details in the textbook. Okay, so now we're at the point where we really are wanting to use conservative vector fields, because that makes integration so much easier. Right? It's like a fundamental theorem of calculus. As soon as we know that the integrand has an antiderivative, then we can evaluate the integral really quickly by just evaluating the antiderivative of the endpoints. So similarly here, if I want to compute an integral of a vector field, it would be really nice to know if it's conservative, because then I just need to worry about evaluating it at the endpoints, the potential function at the endpoints. So how can we check to see, or how do we determine if a vector field is conservative? So this is a test for conservative vector fields. The first direction is just an observation. So theorem 5 is just an observation. If f is conservative, then these mixed partials are equal. So let's see, why is that the case? So I'm writing down that my vector field has these two components. Assuming it's a vector field in the plane. So the vector field xy has p of xy as our x component of our vector field, and q of xy is the y component of our vector field. And we're assuming that they have continuous first order partials. If it's conservative, then the y partial of the x component has to be equal to the x partial of the y component. Why is that? Well, if it's conservative, we know that, maybe I'll put implies, we know that f is equal to some potential function, or the gradient of some potential function. So that means f is equal to some f sub x comma f sub y, where those are partial derivatives, for some f. And this is our potential function. That's what we've called our potential function. So for some f, which is our potential. But if that's the case, then when I take the partial derivative now, I'm thinking of this as, this is our p, and this is our q. So then when I take the partial derivatives, so we'll call it del p del y. That's just the y derivative of that first component. So that's fxy. And del q del x is just fyx. That's del q del x. And they're equal because we have equality of mixed partials from way back in the section where we looked at partial derivatives. So these two mixed partial derivatives are equal, and that means then that the derivative of the y component has to be the y derivative of the x component is equal to the x derivative of the y component. And so if it's conservative, we get that it has to have this relationship. All that is just the equality of mixed partials. The converse actually turns out to be true, and this is the surprising part, that if the mixed partials in this way, so if the y derivative of the x component of our vector field is equal to the x derivative of the y component, then it turns out that that means it's conservative. So this is our test. This is our test for a conservative vector field. It's a nice way to test it. So if we want to know, is our vector field conservative, our first step isn't to go, oh, well, let's see if we can find a little f function so that its x derivative is the first component, so y derivative is the second component. No, we can just say, no, I'm not even going to do that. All I'm going to do is check to see, is the x component of my vector field, when I take its y derivative, is that the same as the y derivative or the x derivative of the y component? And if it is, then we're done. So I'm just going to leave it here that the proof of theorem 6 is delayed to section 16.4, the next section. That's where it comes up more appropriately to prove it. But for right now, we'll just use it. So let's go ahead and do some examples. So here we've got a vector field f, and I want to know, is it conservative? So determine, is it conservative? And if you think about what we've done so far, perhaps the approach would be to, okay, let's see if I can find a little f so that its x derivative is that first component and its y derivative is the second component. That would establish it's conservative if you can find that. But if it isn't conservative to begin with, that sort of leads you down a road that is potentially gets you to a dead end. So it would be nice to know if it's conservative before we even bother searching for a potential function. So that's what we're going to do. We're going to test to see if it's conservative before we even bother looking for a potential function. So let's see, is it conservative? Well, we're going to let this part be our function p, scalar function p. So our x component is p. Our y component we're going to call q. And we're going to take the derivative, del p del y, or in other words, p sub y. When we take its derivative, we get negative 2x sine y minus cos x. Then I'll do the same thing for the next part, del q del x. In other words, q sub x. When I take its derivative, I get a negative 2x sine y minus cos x. And these are equal. So a little exclamation mark. Yes, they're equal. So that means that it is conservative. So it implies that f is conservative. Okay, I need to be a little bit careful here I'll just write it down, conservative. Because I really need that the assumptions are true in the theorem, so I didn't even refer to those. So D is open and simply connected. So that's the region on which our vector field is defined. And if I look at this, these functions making up the two components, they're defined everywhere. So in this case, D is all of R2. All of R2. All X and Y values make sense to plug into our function f. So its domain is all of R2, and R2 is open and simply connected. It's the whole plane. So that's just one thing we need to be aware of, that our region has to be open and simply connected in order for this to work. And it is in this case, it's all of R2. So f is conservative. Now let's see if we can find a potential function. So now we find the potential. Potential. I shouldn't say the potential. I will say a potential, because it's like finding an antiderivative. There are infinitely many antiderivatives because you can add a constant on in the end, and that's still an antiderivative. Same with here with a potential function. We can always add a constant on the end, and it will still be a potential function for it. So it's up to a constant. So now let's find a potential. We use a method we call partial integration. Partial integration, why is that? Because the vector field, now that we know it's a conservative vector field, those components, P and Q, are partial derivatives. So we need to integrate each one of those with respect to the variable it was differentiated with respect to get to the potential function. So we need to do partial integration to get back up to the potential. So partial integration. So here's how we do it. We're looking for a function little f. What we know is that the x derivative of this is that x component of our vector field. So we know this. And we also know the y derivative is the other component, that component q. So we have these two bits. We're looking for a function little f whose x derivative is that and whose y derivative is that. So what we'll do is we will take this first equation and we will integrate with respect to x. So that gives us that f is equal to, so now we'll go ahead and integrate. So the antiderivative is x squared cos y. The antiderivative of cosine is sine, so that's negative y sine x. But because we are integrating with respect to x, there's a constant of integration that comes up. That constant of integration isn't a constant in and of itself, it's a constant relative to x, because x was what we differentiated with respect to. So we get a constant which is independent of x, so a constant relative to x, and that means it could be a function of y. So that's our constant of integration. It's this function of y that could potentially be sitting there, because when I differentiate now this function little f, I get exactly what's sitting there at f sub x. The g of y function differentiates to 0 when you differentiate it with respect to x. Okay, so then we're almost there. We almost have f. Now we differentiate with respect to y, because when we do this derivative, it's supposed to equal that other component that we have written above. So differentiate with respect to y, we get that this is negative x squared sine y minus sine x plus g prime of y. And that is supposed to equal this thing. I'll highlight the exact part it's supposed to equal. It's supposed to equal this bit here. So those are supposed to be equal. And so we scan across and we say, yeah, we got that first part, good. Got the second part, good. Oh, that means that this is supposed to be 0. G prime of y is supposed to be 0. So that means if its derivative with respect to y is 0, it means it's constant with respect to y. So this function is constant with respect to x, constant with respect to y. So that means g is constant. So we could say, like, say g is equal to some k if we wanted to. So that means that our potential function, so maybe I'll say therefore our potential function, oops, let me just get rid of that. I put a bracket too soon. Fxy is given by negative x squared sine y minus sine x plus a constant k, where k is any constant. And so there's our potential function. We just were asked to find a function, so we could take k to be 0. We didn't even need to write k in there. We were just asked to find a function. If we read the question closely, find a function f such that it's the potential for the vector field. So we could take k to be 0. I'll just write that down here.
Your y derivative?
Say that again?
Shouldn't it be x squared cos y minus y sine x?
X squared cos y minus y sine x. Thank you. I wrote down the wrong part. Yes, this bit here. Thank you. Good catch. Sorry, I was looking at the wrong spot. So it's cos and y sine x. Thank you very much. Cos y minus y sine x.
You have a negative in your x squared.
Oh, and I got to get rid of that too. Thank you. Perfect. Thanks very much. So yeah, there's our potential function. So that's I should have been more careful there. That's always a potential spot for disaster. I've already found f, and then that next step was to just make sure we dealt with what g was, and now we've dealt with g, so then we go ahead and write down what f is. All right, thanks for being awake today. All right, so now we've got a method, partial integration, to compute these potential functions. So let's go ahead, I'll leave that some of that exposed still in case you're still writing. So now we can go ahead and do an example like this. Determine the line integral for this vector field where C is a curve from the point 1, 1 to the point 4, negative 2. So notice we're not even given a parameterization for C. So we don't even have a hope of setting up a parameterization for C and then plugging that into our vector field and then working out what dr is and actually setting up the integral, taking the dot product and doing the integration. This is really an indication that if they're not telling us what the curve is from the initial point to the terminal point, then that's because it doesn't matter. And when does it not matter? It doesn't matter when the vector field is conservative. So this is a bit of a hint already telling us that this vector field is probably a conservative vector field. So the first thing to do is, we could check. So what I would do first is I would, take the derivative of the first component with respect to y, figure out what that is, then take the derivative of the second component with respect to x, figure out what that is. And if they are equal to each other, then that's our test for a conservative vector field. So it would be conservative. So if we do this derivative, what is it? It's 2y over x squared, whereas the derivative of this one would be 2y over x squared. Oh, yep, they are equal. So therefore, f is conservative. So we need to find a potential function. So we can go ahead and say, f is conservative. And it is equal to the gradient of f, where, so we could use partial integration here, and you're certainly welcome to do so and try it out, just like we did in the last example. Or if you're, if you got a keen enough eye, you might be able to just eyeball what the function is in this case. So f of xy is equal to, when I take its x derivative, I want to get y squared over x squared. When I take its y derivative, I want to get negative 2y. So in this case, I probably want a y squared up top, because when I differentiate, I get a 2y. Probably want an x on the bottom. That's going to give me, when I take its y derivative, that'll give me the 2y over x. But I need a negative 2y over x. So if I throw a negative sign in front, that gives me the derivative sitting in the y component. When I differentiate with respect to y, I got the negative 2y over x. That was the more straightforward one to see. When I take its x derivative, do I get what's sitting in the x component? Yep, because when I take its x derivative, that x on the bottom becomes an x squared on the bottom, and we get an extra negative sign from the power rule. And so that's our potential function. So we could, if we're lucky, we could eyeball it in some cases. And so this means then that now I want to compute my line integral. So rather than having to do a parameterization approach and all of that stuff, which is the previous section, section 16.2, we now can use the fundamental theorem of line integrals, which says that since this is the integral of a gradient of f dot dr, then this is f evaluated at the point Q minus f evaluated at the point P. And so that's going to be negative 2 squared over 4 minus, and then negative 1 squared over 1. Or in other words, it's going to be 4 over 4, so negative 1, and then we've got a minus, and then the 1 squared over 1 is 1, so we've got a minus negative 1, and in which case we get a value of 0. As a 1 plus a 1. So that's how we can use this fundamental theorem of line integrals. And the other results in this section were all about, conservative tests. What's the equivalent between, if you got a conservative vector field, it means the integrals are path independent. It means the integral around any closed curve is 0. How do you check to see if it's conservative? Look for the partial derivatives, the y partial of the first component and the x partial of the second component. See if they're equal. If they are, then it's conservative. And so you know that you can search for a potential function. You can compute it using partial integration if necessary. And then that makes computing these integrals much easier. So we're going to end on this section on this last example. And then I'm going to make a mention about what 16.4 is about, just so you have context. We'll do it on Wednesday, but I want you to have context about what 16.4 is about, just so you know what the next steps in this are really. So
Professor, could you go back to the previous example for a second?
Sure.
Thank you. So here in f of xy equals negative y squared over x.
Yep.
Yeah, so right there. How did you get that exactly?
So how did I get the potential?
Yeah.
I just eyeballed it. So as I said, you could use partial integration. So if you don't see it, go ahead and use partial integration. Just exactly like we did in the previous one. Say, okay, that's supposed to be a derivative with respect to x, so I will anti-differentiate it. And when I anti-differentiate it, I get a negative y squared over x. And then there's plus something that is a constant relative to x. So that would be the g of y. And then you differentiate that, and you'd get that g prime of y has to be 0. So you could use the partial integration, just immediately follow the steps that we did in the previous example for this one. However, in this case, I just eyeballed it. And as you do these things, you'll start to be able to eyeball them. You just say, okay, I want something whose, when I take its x derivative, gives me this, and when I take its y derivative, gives me this. And so I know that it's got to be a y squared up top, because its y derivative is going to be 2y. And I know it's got to have an x on the bottom, because when I take its x derivative, there's an x squared on the bottom. And so you can just reverse engineer what the potential function is. I'm not saying that this is the best way to do it. I wanted to give you a contrast. So there's the partial integration way, which is foolproof, always works. Use it whenever you're unfamiliar, or it looks like you can't figure out what the potential function is without some structured approach, partial integration. However, in some situations, it'll just be screaming at you in the face. It'll say, this is what I am. This is the potential function, and you can just jot it down.
Jamie, should we do this on exams? The by inspection method?
Unless it says use the method of partial integration to find the potential function. If it doesn't say that, yeah, you can just write it down. That'd be no problem.
Okay.
So you can eyeball it. It's best to show your work when asked to show your work. So for example, use a method of partial integration. That's really saying show your work as to how you found it. But if it's caught up in the context of a problem like this, where it's just saying determine the integral, you can go ahead and jot down the potential function if you can eyeball it. If you can't eyeball it, no worries, just go through partial integration to get it.
Hey,
Good
Professor?
question. Yep.
I have one more question. So why did you not integrate with respect to y?
Why did I not integrate with respect to y to get that?
Yeah, so you just
get-
integrated with respect to x, like the I value.
You can integrate with respect to y, right? If I integrate with respect to y, negative 2y over x dy, then what I get is, so I'm looking at that, oh, sorry, there's a negative sign there, yeah. So when I integrate with respect to y, I get negative y squared over x plus a constant relative to y. So there would be a plus a g of x there. And then I differentiate with respect to x. Actually, I should be writing a partial derivative here. Then we differentiate with respect to x. And I'd get a differentiating with respect to x would give me a y squared over x squared plus g prime of x. And then I would compare that with this and say, oh, that's got to be 0. And therefore, this has to be a constant. And that gives me the right spot, or the right thing I'm looking for. So you can do either way. Partial integration doesn't say you always have to integrate the first component with respect to x and then differentiate to compare with the second component. You can do the opposite. You can say, well, I know that this component here, the second component's got to be a y derivative. So I could integrate with respect to y and get the function that way. So I mean,
Okay.
there's no hard and fast rule here. All I'm saying is that first component's an x derivative, that second component's a y derivative. So figure out what the function is. And do it however you want. Partial integration is the technique, but it's not dictating the order you have to do it in. Does that make sense?
Yeah, thank you.
You're welcome. So this last example is asking us to show that the partial with respect to, so the first component's partial with respect to y is equal to the second component's partial with respect to x. So let's just jot down what this is. This is negative y over x squared plus y squared. I'll write it just in terms of the components like this so we can see exactly what the components are. So that's our vector field. And we want to show that the y derivative of p is equal to the x derivative of q. So again, this is p, this is q. So when I go del p del y, the derivative with respect to y is the derivative of the top function. So that's negative 1 times the bottom, x squared plus y squared. So I'm using the quotient rule here, minus the top times the derivative of the bottom, all over the bottom squared. And so this gives me, there's a 2y squared minus a y squared, so that gives me a y squared minus an x squared all over x squared plus y squared. And then we'll do the same. The derivative with respect to x is the derivative of the top, which is 1 times the bottom minus the top times the derivative of the bottom all over the bottom squared, which is equal to y squared minus x squared all over x squared plus y squared. And we notice then that these are equal. So we, at momentary celebration is, yeah, they're equal. Okay, so this is conservative. Ah, there's a problem there. It's not conservative. Okay, how would we know that? Well, the first thing is this part B is telling us to show that this is not independent of path. So it's not independent of path. And so how are we going to show that? I'll do this quite quickly because we are in the final minute. So I will just consider the unit circle. And the way I'm going to show it's not independent of path is I'm just going to show that the integral around a closed curve is not zero. So we're going to consider the unit circle. R of t is equal to cos t sine t 0 less than or equal to t less than or equal to 2 pi. So we are integrating around a unit circle. And when I do that, we are going to go through and do our calculation. So our calculation is going to be the integral from 0 to 2 pi, the vector field, which is written down up at the top, with cosine and sine plugged into it. So that would be negative y over 1. So that's negative sine t. And then x over 1. X squared plus y squared is 1 because I'm using a unit circle. So that would be x dotted with r prime, which is negative sine t cos t, and that's dt. And so this is going to be the integral from 0 to 2 pi of 1 dt, because the dot product of these would be sine squared plus cos squared. And so this has a value of 2 pi. And since it's not 0, that implies that the integral is not independent of path. It's not independent of path. So even though the partials del p del y and del q del x were equal, it turns out that this is not a conservative vector field. If it was conservative, then this integral would be 0 down at the bottom. Integral around a closed path would be 0, but it's not. So it's not independent of path. That means that f is not conservative. So we have to think, why do our results from before not imply that f is conservative? So I'm going to scroll back and see what was the result that told us it was conservative. So it was theorem 6. Theorem 6 says that if you are on an open and simply connected domain and these derivatives are equal to each other, then it's conservative. This is the key word here, simply connected. The domain had to be simply connected. When I look at the example, the domain is all of R2, but I have to remove the origin because that would cause division by 0. And this is not simply connected then because there's a hole in it. The origin has been removed, so not simply connected. And so theorem 6 doesn't apply. Even though the partials were equal, theorem 6 doesn't tell me it's conservative because the hypothesis wasn't satisfied. All right, so that's it for this section, and that's it for the material that's going to be on the final exam, the examinable material. Next day, we will go into section 16.4 and see how it's related to this stuff. It just takes this idea just one step further. So I'm going to stop the recording now.